So in section 2.6, we're going to work more with transformations and functions. We're going to add to our collection of transformations and things that we can do to our functions. We're going to start with a little bit of review here, some horizontal transformations. And I don't think this is really anything new. Transformations. What's new is the notation here for it and how we regard these things or how we write them. So let's start with some notations. Y equals f of x plus c and y equals f of x minus c. So this is writing it in a little more abstract way. And what this refers to is a shift to the left by c units. So shift left by c. What do you think this is going to refer to? Shift to the right by c. And like I said, I think this is new. What's different is the notation. So let's look at a couple of problems here. For instance, problem number 34 asks us to look at the function f of x equals x plus 1 squared. Well, I'm hoping that's familiar. How has this been shifted compared to a more familiar function, say f of x equals x squared? Yeah, to the left by 1. And you can see what you've done is you've taken and plugged in x plus 1 in for f of x. So this has been shifted to the left by 1. In a similar way, we can look at problem number 36. F of x equals the square root of x minus 4. Now, this is assuming that you know what the square root of x looks like, but even if you don't, you can tell how this graph has been shifted compared to the square root function. How has this one been shifted compared to your square root function? So the minus here, for your horizontal shifts, the shift actually goes kind of opposite of what that sign might suggest. So a minus would mean to the right, a plus would mean to the left. This has been shifted to the right by 4. Shifted. If there was a negative on the outside, that's going to cause a flip in the graph. But it's not going to affect the way it's shifted. So shift to the right by 4. We can take a quick look at these Desmos. So Desmos, cut that one off. Let's take a look at y equals the square root of x and y equals the square root of x minus 4. And let me move this around a little bit. And you can see it's been shifted to the right by 4. So not a big surprise there, and like I said, a little bit of review. But let's try and make this a little bit different with the next problem, and that is problem number 8a. So you have some graph of f of x, and I don't think it's even really specified in the problem, but they want you to describe how the graph of f of x plus 5 would look in comparison to the graph of f of x. So if you knew what the graph of f of x is, how would the graph of f of x plus 5 look? Yeah, thank you. Shifted to the left by 5. Shifted left by 5. Great. So a little bit more abstract, but still workable. Yeah, please. Yeah, this one was shifted to the left. Essentially, this is the same thing because what we're doing in problem number 34 is we're really looking at this graph And then if you plug in x plus 1 in here, you get this function, x plus 1 squared. But by putting in the x plus 1 here, that causes a shift to the left by 1. Let's look at some vertical shifts. So some vertical transformations. So y equals f of x plus c, and y equals f of x minus c. What do you think the plus c and minus c are going to do in this one? Up and down. Is the plus c going to be a down or an up? Up. So your vertical shifts happen like you would expect. Plus is up, minus is down. So that's kind of nice. And again, let's take a look at a couple review problems and then a couple that are a little bit on the newer side. So problem number 30. F of x equals x squared minus 4. How's that one been shifted? Good, down 4. And 46, kind of a couple things going on here. F of x equals square root of x plus 4 minus 3. And I wrote f of x, I think the problem actually wrote y, but the shift is still the same. Two shifts, in fact. What are those shifts? Good, to the left by 4 and down by 3. So left by 4 and down 3. Nice. So let's take a look at problem number 12 then. So same kind of thing, but we're going to start using this f of x notation. So problem number 12a looks like this. Got the graph of y equals f of x plus 3 and plus 2. Thank you, Lucas. Shifted to the left by 3 and up by 2. Left by 3, up by 2. Yeah, go ahead, please.
Will there ever be an instance where it actually will go to the right because it's positive?
Not like this. Positive in here is always going to be to the left. You know, well, there's, no, I'm going to stick with this. If you have a plus 3, that's always going to shift your graph to the right. Or, excuse me, to the left by 3 inside the parenthesis. Even if you had something kind of strange.
I was told to think about what would make it 0, so negative 3 plus 3 would be 0.
Yeah.
So it's,
And that,
x is negative when you're shifting it to the left.
so that's exactly what I do when I try and give people a little bit more insight into why a plus would cause a shift to the left by 3. And I look at the graph of y equals x squared. Now, the important point on the graph of y equals x squared is right here, at 0. So if I wanted to look at the graph of, say, y equals x plus 3 squared and wanted to know how it's shifted, what I could think of is, all right, well, where is this point going to be? Well, I get this point when I square 0, just like Jeff said. So where do I square 0 for what value of x? Well, what do I put in here to get a 0? What value of x? What plus 3 equals 0? Try again. What plus 3 equals 0? What value of x? Negative 3. So 1, 2, 3. So this point here is going to occur here in this graph. So you're going to get a graph that's been shifted to the left by 3. So that's why these shifts run kind of counter to what you might expect. And in a similar way, you could look at, for instance, y equals x minus 2 squared. What value of x is going to make that 0? Well, x equal 2. So this graph is going to be shifted to the right by 2. Okay, yeah, I mean, what you have to kind of avoid is trying to distribute that square and saying that's x squared minus 4, because we can't really work it like that. All right, does that help explain the horizontal transformation a little bit for you? Okay, good. Let's take a look at part B then. Part B says y equals f of x minus 7 minus 3. So take a second, think about that, and let me call on somebody. Kenny, what do you think? How's that one been shifted? Good, right by 7 and down by 3. Perfect. So again, that horizontal shift is opposite of what the sign might seem to indicate, and then the vertical shift is exactly what the sign does indicate. So how are we looking with your horizontal and vertical shifts? Okay? It's a good question, because when you're putting things into the function, you're changing the value of x that you put into the function. So for instance, if I put in x equals 7, before I even put it into the function, I subtract 7. So I get 7 minus 7 is 0. So before I even put that value of x into the function, I change it. So I'm changing x, which is your horizontal component on the x-axis. But after I evaluate the function, I find what f equals, then I subtract the 3. So this is really your y-coordinate, and then I subtract 3 from the y-coordinate or add 3 to the y-coordinate, whatever the case may be. So you're changing the y-coordinate. And that's just going to change it directly as you see the sign. So if f of this number was 10, well, 10 minus 3 would be 7. So I'd be shifting it down by 3, as opposed to adding 3 or subtracting. Whatever you do to the y-coordinate, you're going to see the graph shift appropriately. So, great questions. Let's keep going with some other kinds of torture that we can do to our graphs. And that would be some stretches. So, for that, let me kind of demonstrate things this way. Let's take out our graphing calculators. And let's enter in a function. Let's go with a familiar one. F of x equals x squared. So x and then squared. And let's type in a couple other functions, like a 2x squared or a 3x squared. Now for myself, when I'm graphing these things, because I got the nice fancy color ones, I can see, based on what color I have, which graph I'm dealing with. As far as the window is concerned, let's do this. Let's set up our window from, say, -4 to 4 on the x-axis and -16 to 16 on the y-axis. That should be good enough. And let's graph it. So there's our first graph, y equals x squared. Here's y equals 2x squared. And then y equals 3x squared. What happens as I increase the value of that coefficient? Yeah, it's getting narrow. Essentially what's happening is it's getting stretched up. You're pulling it away from the x-axis when you do that. Let's throw in another one here. Let me ask for some predictions first. Let's do 0.5x squared. What's that going to do? Yeah, it's going to open wider. It's lazier. You're pulling it down towards the x-axis. So yeah, you've got a much lazier function now. Let's see. So in general, there's really a couple different kinds of things that can happen depending on the value of C. So these are your vertical stretches. Vertical stretches. So y equals c times f of x. If c is greater than 1, then the graph is going to be stretched away from the x-axis. It's going to be made taller. Then the graph will... I don't think that I could write a textbook and get away with this. We can do it in class. We'll get taller. It's going to be stretched away from the x-axis. I want to use terms closer to that for our horizontal stretch. Now there's another case. So the case when C, that number is bigger than 1, you're going to get stretched away from the x-axis. It's going to be stretched up. If C is between 0 and 1, then what happened? What happened when we had 0.5x squared? Yeah, it got wider. And really effectively what you're doing is you're pulling it down towards the x-axis. You're grabbing it and putting some weights on it, pulling it down. So if C is between 0 and 1, the graph will get pulled down toward the x-axis. So a couple different possibilities there in terms of your stretches. I think the book used C as well. Yeah, so H and K, those are kind of probably going to be used for parabolas and stuff like that when we're talking about the vertex. So here's a nice demonstration of what's happening when you stretch or shrink a graph. So when C is greater than 1, that graph's going to get taller. You're pulling it away from the x-axis. When C is between 0 and 1, over here, that graph is getting shrunk. You're pulling it down towards the x-axis. So now when the graph is 0, it's not going to change. So it's not going to change the roots or x-intercepts of your graph, but it is going to change the height of your function. Let's do a couple quick examples. Problems like 44. So y equals 1/2 times the absolute value of x. Well, the absolute value, I'm hoping that's a familiar graph for you. Yeah, it's that V shape with a little point at the vertex, right? But what's going to happen when we graph 1/2 the absolute value of x? Yeah, it's going to be shrunk or pulled down towards the x-axis. In fact, it's not a bad idea to graph this one again on our graphing calculators, mostly as an excuse to remind you or teach you where to find the absolute value. So let me clear out all these old functions. To find the absolute value, press the math key, and then over to the right once. Does it look like there's something promising here? Yeah, absolute. Now, depending on your operating system for your calculator, you might get some absolute values You might get something that just says ABS with parentheses. But either way, it's going to graph the absolute value. I want the absolute value of x, and then 0.5 times the absolute value of x. I'm going to change my window for this one. I don't think I need to see this between negative 16 and 16 anymore. So I'm going to go from negative 6 to 6, and from, let's see, 0 to 4. So there's one graph, there's the other. So the graph of the absolute value has been pulled down or shrunk because of that factor of 1/2. Perhaps another way to understand why it's affecting the graph as it is would be to hit the trace key. And let's trace a couple values. Let's trace what happens at x equals, say, 4. At x equals 4, on the graph of the absolute value of x, I'm up here at 4. The absolute value of 4 is 4. But if I take a look at my other function, press the down arrow key, when I'm on the other function, I take the absolute value of 4 and multiply it by half. Half of 4 is 2. So that y coordinate is getting cut in half, and that's why it's pulling it down towards the x-axis. Let's try problem number 10b. Y equals 1/3 of f of x. How's that 1/3 going to affect the graph? Yeah. Exactly. So this is again going to get shrunk towards the x-axis. So if I had a value of 9 for f of x, then it's going to be 3 when I evaluate this function. So I'm going to divide all these y coordinates by 3. It's going to shrink things down to the x-axis. So we'll shrink the graph. So you're going to divide that graph by 3. There's a couple other interesting transformations that we can do to our graphs. And these are going to start to be a little bit newer, at least a couple of them. So we've done horizontal transformations, vertical transformations, vertical stretches. The next one we want to do is a horizontal stretch. So horizontal stretch. So that's y equals f of c of x. So again, your horizontal changes come when you put your constant in here into the argument of the function. So it's a constant times x. Now let me show this one here on Desmos. And it's not a function that you're going to be familiar with, but I think we can try and appreciate what its effect on the graph is. So it's a function we're going to borrow from trigonometry. It's called the sine function. Kind of a handy one. It's a nice wave function. But the question is, what happens if I put something in there? What if I put in, say, y equals, say, sine of, I don't want capital S, sine of 2x? How is that going to affect the graph? Yeah, it's shrinking it along the x-axis. It's kind of pulling it in. And maybe if I can animate this, let's put a C in here. So think of it like a slinky. If you have, sine of x is stretched out, then by putting in values of C, you're really compressing that slinky. Let me try and, like I said, animate that. So, can you see the? Here, can you see the effect of changing the value of C? You're compressing it or stretching it, but you're changing the graph horizontally. So that's C equals 1. If C is less than 1, then I'm really stretching it out. If C is greater than 1, then it compresses it. So I can do whichever I want depending on the value of C. So let's kind of summarize that. So if C is greater than 1, the graph gets compressed horizontally. So that's one possibility. If C is between 0 and 1, then it's going to get stretched horizontally. If C, or excuse me, 0 is less than C is less than 1, the graph gets stretched horizontally. Now, this is something that I'm not really going to be too demanding about, because I think the best places to see this kind of a change is with the trig functions that I use to demonstrate this. And this is not a class in trigonometry. I think most of the stuff that we're dealing with, you know, it's hard to see those kind of stretches. But let's just practice with maybe a couple of them. We'll start with problem number 18a. So if I have the graph of f of 2x minus 1, let's see what kind of changes this is going to have compared to the graph of f of x. Let's start with the easy part. What's the minus 1 going to do? Yeah, shift it down 1. Down 1. How about the 2 in here? Yeah, it's going to compress it. Compress. Or and let's try problem number 18b, which, you know, it'd be really nice to have actual functions that worked well with this, but we're kind of hamstrung a little bit in this class. There's two things that are going to happen this, and they kind of, I don't know, depending on the function, they could actually almost cancel each other out, but that'd be a pretty well-tailored function to do that. Let's start outside the parentheses, or outside the function. What's the 2 going to do to the graph? Good, stretch it vertically. So stretched vertically. How about the 1/2 in there, Erica? It'd be a horizontal stretch. It depends on the function. If this was like the absolute value function, then they would cancel each other out. Horizontal stretch. So for giggles, let me just do this with a trig function just to see what that would look like. So really what they're asking is to put, say, a 2 outside, so 2 times the sine of 1/2 x. So with some functions, it's not going to cancel out, and the sine function here is one of them. So you can see the vertical stretch, the height of these things is a lot taller. It's up to 2 and down to -2. And the horizontal stretch means that instead of repeating itself every 2 pi units like the graph here in red, the graph in blue repeats itself every 4 pi units. So it's been stretched horizontally and stretched vertically. So, all right. At least you've got a little preview of some of the stuff that might be heading your way with a trig class. All right. Let's take care of the last little bit of this stuff, and that is some flips. So the last little piece of abuse that we're going to do to our functions is we're going to flip them. There's 2 flips that we can do for our graph. Y equals negative f of x, and y equals f of negative x. And one thing that you can kind of get used to is this. When you're doing something outside of the function, that is outside of f, that's going to affect things in terms of the y coordinate. Inside is going to affect things in terms of the x coordinate. Now negative f of x. Think of negative x squared. What happens when you look at the graph of negative x squared as opposed to the graph of x squared? Yeah, flips it upside down. So, okay, this is gonna flip the graph around the x-axis. Flips the graph around the x-axis. What do you think the negative inside the absolute value, or inside the function, is going to do? Flip around the y-axis. Yeah, flip around the y-axis. So let's take a look at a few examples of this. Problem number 38, y equals negative the absolute value of x. So the absolute value, usually kind of a triangle with its vertex pointed down, sitting on the x-axis. This time, though, graph of negative the absolute value of x, it's going to be inverted. It's going to be reflected around the x-axis. Reflected around the x-axis. In fact, we can draw that one pretty quickly. So it's just going to be something like this. But it's nice to be able to predict that based on the form of the graph, form of the equation. How about problem number 50? A couple things going on with problem number 50. We've got y equals 2 minus the absolute value of x. And sometimes when you're looking at these, it might help you out if you rewrite them a little bit in order to get a handle on what's going on. And in this case, I'd rewrite it like this. Negative the absolute value of x plus 2. I don't know. To me, this looks a little bit easier to judge. Because now I can take a look at these things and figure out, oh, all right, what's happening because of this? It's been flipped. What's the plus 2 going to do? Good. Flipped, and then up by 2. So basically, if I wanted to graph that one, I could extend this graph up a little bit, and then take that one and flip it, or take the absolute value, flip it, and move it up 2. So here's your graph of y equals negative the absolute value of x plus 2. Let's try some other kind of flips and things. And we'll look at problem number 39. So typically I don't take your homework problems away from you, but hopefully you won't hit me too hard on the evaluations, that complaints that I'm doing your homework for you. And I know it's tough to swallow. Take a look at the fourth root of negative x. Now the fourth root is probably not a graph that you're terribly familiar with. So let's see. How do I want to do it? Tell you what, let's do it on our graphing calculators again. So we'll clear out our functions here. And let's see. To get the fourth root, press the math key, and then the fifth option down gives you an option for whatever root that you want. And you know what? I made a mistake here. I need to type in the number first. So go back to the y equals key, type the number 4, and then hit the math key. Go down to option 5, and that 4 now becomes the fourth root of x. So there's the fourth root of x. Let's graph that between, say, negative 16 and 16 on the x-axis, and that'll probably go between 0 and 2 on the y-axis would be fine. And I get something that looks like this. Okay, great. In comparison, let's graph the fourth root of negative x. So again, type the number 4, hit the math key, fifth option down, and then negative x. When you're typing in that negative for negative x, use the opposite key on the bottom of your calculator next to the decimal point, not the negative key. But when you press the graph key, you're going to see a mirror image. And what's happened is that this graph has been reflected across the y-axis. I use the window from negative 16 to 16. Now, a lot of these, they ask you to sketch the graphs, etc. We're going to rely on just using our graphing calculator here. But let's try one more like this. Try and figure out what changes have been made. And that'd be problem number 22b. So 22b is y equals the square root of negative x plus 1. Now the square root of a function might be something you're a little bit more familiar with. Its graph is kind of like half of a parabola that faces sideways. But there's been two changes to that graph. What are those changes? I'm trying to remember, is it Matthew? Michael. Good. So it's been flipped around the y-axis and shifted up by 1. So let's take a look at two graphs. Let's take a look at the graph of the square root function and then this one. So let me enter both of those. So go back to your y equals key. Let's enter the square root function, square root of x, and then the square root of negative x plus 1. Make sure that when you enter in that plus 1 that you're not under the root anymore, because that would cause a much different shift. We'll keep our window the same. Let's see. Well, maybe I can bump up the y max to, say, 5. So there's a graph of your square root function. And two things have happened here. It's been flipped around the y-axis and it's been moved up by 1. So, cool. Thanks, Michael. Here's a little trivia question for you. Not exactly a trivia question, but here's a little thought question. Let's take a look at the graph of x squared, and if I wanted to reflect this around the y-axis, I would graph negative x in parentheses and then square that. So let's take a look at those graphs. Oops. Let's change my window a little bit. Let's go between, say, negative 4 and 4 on the x-axis and 0 and 16 on the y-axis. So there's the first one, and there's the second one. I don't see much of a difference, do you? Is there any difference between those two graphs? Not really. In fact, they're the same, right? Does it matter if you square x or negative x? You're going to get the same thing either way, right? If you square 5, you get 25. If you square negative 5, you also get 25. So this is what's called an even function. It's even because it's symmetric with respect to the y-axis. So let's talk about even and odd functions. The last little piece here. Do I want to do... You know what? Let's hold off on even and odd function for just a minute. Let's do some more practice with some of what we've just done in the form of problem number 70. There we go. Zoom out a little bit. Okay. So in problem number 70, they're giving you this function is f of x. Let's see if we can't figure out what some of these other graphs would look like based on the graph of f of x. This is a good problem. I like it because it's just asking you to think about what these transformations are going to do, how your function is going to change, what's going to look like. So let's start with part A. What's going to happen to the graph of f of x if I do 1/3 f of x? Yeah, it's going to shrink the graph, right? So it's going to be 1/3 of the height. It's getting pulled down towards the x-axis. So part A, the answer would be 2. Let's go in order. Part B. Two things happening to part B. What are they? Emily, what's one of the things that's happening in part B? All right, good. It's going to be flipped around the x-axis. Flipped into the left 4. Well, the way I'm looking at this, I only see one of these graphs that looks like it's been flipped. And if I look a little bit closer, it looks like it's been shifted to the left by 4. So what would that be? Which number? 3. Good. So this one's been flipped, faces up instead of down, and it's been shifted to the left by 4. Cool. Let's keep going. F of x minus 4 plus 3. Minus 4 and plus 3. Good. To the right 4 and up 3. To the right 4 and up 3. Looks like a 1. And kind of by process of elimination, what happens if I look at f of negative x? Katie? Good. It's going to be flipped around the y-axis. So just kind of a mirror image right here for number 4. Nice, nice, nice. Let's do a problem like 58. 58 and 62. F of x is the absolute value of x. Reflect in the x-axis, shift 4 units to the right, and shift upward 3 units. So 3 different things happening here. Let's put them all in one function. Call it g of x. So I'm going to reflect it around the x-axis. What's going to do that? Yeah, negative sign in front. And and then shift 4 units to the right. So x minus 4. And last but not least, shift up by 3. Plus 3. Thanks, ladies. Why don't you try problem number 62? Shrink vertically by a factor of 1/2, shift to the left 1 unit, and shift up 3 units. So see what you can do with problem number 62. Andrew, what you got? One half. Well, what's in the absolute value? We want to shift it to the left 1 unit. Good. Plus 1 and then plus 3 there. So overall, g of x is 1/2 the absolute value of x plus 1 plus 3. The half is on the outside, yes. Yeah, that's what's going to cause a vertical shrinkage. If it was on the inside, then it would be a compression. So it'd be a much different looking function there. Nice. Well done. All right, let's wrap that up for homework. In section 2.6, homework, try 7 through 69, 7 through 73 in homework.